In this video we're going to use integral calculus with kinematics, and kinematics is the maths of motion and movement. So for all you people studying physics, you know that kinetic energy is the energy of movement, so kinematics is the maths of motion and movement. So we've already looked at kinematics before. We've talked about displacement or distance, velocity and acceleration, and to go from displacement to velocity you differentiate, so you find dx dt. To go from velocity to acceleration you also differentiate, so you go from you use dv dt to find your acceleration. We now know that the opposite of acceleration is integration, so going back the other way from acceleration to velocity to displacement, we integrate. So to go from acceleration to velocity, you integrate the acceleration and you'll get velocity. And then if you integrate your velocity, you'll get your displacement. Now, you'll need to be aware that when you integrate, if you're just using an indefinite integral, so if you're just integrating the formula itself, you need to remember that you're going to get the velocity formula kind of with some c, and that you'll need to substitute in some values that you know, something that you already know about the velocity, to be able to find the c value. Okay, and the same goes here if you're doing an indefinite integral with velocity, you'll get out your displacement formula but with a plus c. Okay, so let's have a look at kinematics and the graphs of kinematics. So the first graph we're going to look at in our kinematics and graphs of functions is our displacement function. So we're going to graph displacement or distance against time, and we get some kind of lovely function that I've labelled x of t. Now on this graph, if you want to know the displacement or the distance at any time, you just read the points off the graph. Okay, you can also get your velocity from this graph, because velocity is the derivative of displacement, and the derivative of the displacement graph, x dashed of t, is the gradient of that tangent at that point. So if you want the velocity at a particular point, you'll find the derivative and substitute in. Okay, so if you want the velocity at a particular point on a displacement time graph, you'll find the tangent and its gradient, or you will find the derivative and substitute it straight in. If you want the average velocity, you'll choose a point on one point on the curve and the other point on the curve, and you'll find the average slope of that line. You'll find the slope of that line for your average velocity. Okay, so that's your displacement versus time graph. The next one is the velocity versus time graph, and it's the one that's got everything in it. Okay, so if you graph velocity versus time, you'll get a nice curve. Here's one I just made up. Now, for a velocity graph, if you find the slope of the line at any point, the gradient of the slope of that line will be your acceleration. Your acceleration is the slope, the derivative of the velocity time graph. The other thing that you can find, now we know that if you start with velocity and you integrate it, you get displacement. What that means is, for a velocity time graph, if you integrate it, if you integrate velocity, it's like you're finding the area underneath the curve. So the area underneath the curve between 2 points A and B when the curve is a velocity graph, it will give you the total displacement that occurred between time t equals a and t equals b. Okay, so on a velocity graph, the gradient, the points on the curve give you the value for your velocity. The slope of the line at any given point gives you the acceleration. And the area underneath the curve gives you the distance that the thing has travelled, or the total displacement for that given time period. And then finally, we look at the acceleration time graph. And so we have acceleration on the vertical axis, time on the horizontal axis. And so this is our acceleration curve. So that should say a of t. And we know if we integrate acceleration, then we get the velocity. So if we integrate acceleration, we get velocity. And so if we have an acceleration graph, if we integrate, we'll find the area under the curve, and that will be the total change in velocity between t equals a and t equals b. Okay, so let's do some kinematic questions. Okay, so here's an example. A particle starting at rest, that's going to be important, is accelerated according to the formula a equals 4t times 2 minus t, where a is measured in meters per second squared. Find the formula for the velocity v at any time t for the particle. Then sketch the graph of v of t, and hence find the total displacement of the particle in the first 4 seconds. Okay, so first thing we're asked to do is we are asked to find the velocity, and we're given the acceleration. We're also told that the particle starts at rest. That will be important. And we're also told that our units are meters per second squared. So that will all come in useful in just a minute. Okay, so let's do this. Now we have that velocity is the integral of acceleration, and we don't have any end points on that. So when we go and we substitute in our formula and then integrate that formula, so we'll have to expand the formula out to be able to integrate it. When we integrate it, we get plus c on the end. And so our formula has a plus c. So our velocity formula, v of t, has still got a c on the end. So we don't actually have a complete formula. So what we're going to need to do is we are going to need to use some of the information that we got from up above. So I've highlighted 3 bits of information up above. The particle started at rest, the formula for acceleration, and the units. So we're going to use the fact that the particle started at rest. Okay, so to find the c, we're going to use any information in the question about the velocity. And in the question we're told the particle starts at rest. That means when t is equal to 0, when it starts, the velocity is equal to 0. And so we can substitute t equals 0 into this equation here, and v equals 0, and that will allow us to find the c. So that's what I've done here, and what you end up with is c is equal to 0. Doesn't really feel like it's worth the effort really when you get c is equal to 0, but you always need to check. And so what that gives us is that our velocity formula is that formula there. That's our velocity formula. That's part A done. Part B asks us to sketch the graph. Now, this is a difficult graph to sketch, and so I'm just going to go ahead and I'm going to sketch it using my CAS calculator. And also using the CAS calculator, just so that we've got all the information that we need, I'm going to find all of the important points on the curve. So I went and did that earlier. Here's one I prepared earlier. That's what the function looks like. So we're asked to sketch the function. Well, there it is. So we're asked to sketch the function between 0 and 4, and I found the end points, both of which are included, which is why I could find them. And I found them on the CAS calculator by asking for a minimum around this area and asking for a minimum around this area. This, of course, is the maximum, and this is one of the zeros. So there's my graph there. And interestingly, we have some positive values for our velocity. Let me just write this here. Let's write this as v of t. If I was asked to sketch this in the exam, I would just make sure that I am using, oh, see, I've done it already, that I am using t's and not x's. You have to be so careful. Labeling, make sure you're labeling the graph correctly. So this axis here would be t, and this axis here would be v of t. Okay, there are marks awarded in the exam for making sure that you've got your coordinates written as coordinate points with the brackets if they ask, and a comma in between, and that you're using the correct variables. So make sure you watch out for that. You saw how simple it was. I just did it right then. Okay, so final question. Final part of the question was, hence, that's because we needed to find that we had negative areas. Find the total displacement of the particle in the first 4 seconds. So what we had was a velocity time graph, and they want us to find the displacement. So we're going to need to integrate this function. And we've got a positive area, and now we've got a negative area as well. And so we're going to need to integrate those two pieces of the function separately. And so there we go. Our displacement is equal to the integral from 0 to 3, because that's the positive section. And then we need to turn this section here, this very long skinny section here, into a negative value, because I'm just going to use my CAS calculator to do it. So I've put a minus sign at the front. If you wanted to put a plus sign and flip the terminals, you could do that. If you wanted to do plus the absolute value, you could do that. Completely up to you how to do it. Then I use my CAS calculator to work out the two areas. So the first area, the positive area, this section here, is 9. And then the second section from 4 to 3, which is this long skinny bit here, is also 9. And so our total area ends up being 18. And our units for displacement, because our units for acceleration were meters per second squared, the distance units or the displacement units in this unit here are meters, and so our displacement answer will be meters. And finally, one more example. A person throws a ball up into the air with an initial velocity of 12 meters per second. That's probably going to be important. Let's underline that. Initial velocity of 12 meters per second. Gravity causes the acceleration of the ball to be minus 10 meters per second squared. The acceleration of the ball is going to be minus 10 meters squared per second. At what time does the ball reach its maximum height? And then what distance does the ball travel upwards? Okay, So imagine a person is throwing a ball up into the air, and the ball goes, let me draw a little person. Now you know why I teach maths and not art. The ball goes up into the air, and then it turns and falls and lands on the very bumpy ground. So when they initially throw the ball up at this point here, the velocity is 12 meters per second. And then gravity is pulling on the ball the whole time, and the acceleration is minus 10 meters per second. So the acceleration is in this direction, minus 10 meters per second. At what time does the ball reach its maximum height? So its maximum height is up here. And one of the things that we need to know is that when it's at its maximum height, it stops moving. At its maximum height, velocity is equal to 0. So we can use that to help us to find how long it takes for the ball to reach that maximum height. So, solution, part A. At maximum height, the velocity is equal to 0. And the ball has an initial velocity of 12 meters per second. So that also tells us at t is equal to 0, v is equal to 12. So to find velocity, the only thing we've got really is an initial velocity and an acceleration. So because we've got an acceleration, we can find a formula for velocity from that by integrating our acceleration. Now you might think there's no formula for acceleration there to integrate, but there actually is, and the formula is minus 10. So you just put the number in, straight up minus 10. When you integrate that, you get minus 10t, and of course, because we're working with an indefinite integral, we get the plus c. This better not be 0. Okay, so to find the value of c, we're going to need to substitute in a time when we know what the velocity was. So we know that the ball had an initial velocity of 12 meters per second. That means when t is equal to 0, v is equal to 12. And so I can take those values and I can pop them into my velocity formula. So my velocity formula was v of t equals minus 10t plus c. So our velocity was 12, our time was 0 at the start. Substitute those two things in, and we get not 0, we get c is equal to 12. And so our formula for velocity now looks like this, minus 10t plus 12. So now we've got something to do. So now we've got a formula for velocity. We know at the maximum height, the velocity is 0. So now we can go ahead and say, for that formula, if velocity is 0, so we're going to put a 0 here, and solve this equation to find t. And when we do that, we get t is equal to 1.2 seconds. So that's how long it took for the ball to stop moving upwards and reach its maximum height. Okay, part B. Part B says, what distance does the ball travel upwards? What distance does the ball travel upwards? Okay, so distance is displacement, and we've got a formula for velocity. And so we can find our displacement or our distance from our velocity formula. So the distance travelled upwards we can find by integrating our velocity. Now again, we've got a definite integral here. And so we are going to get, when we integrate that, we're going to get a plus c, and so we are going to need some information from the question to help us to find that value of c. So what can we use? What do we know about a given distance at a particular time? Well, what we do know is that at the start, the ball hadn't moved at all. So at the start, the ball hasn't moved. So at t is equal to 0, the ball has moved no distance at all. So at t is equal to 0, at the start, t equals 0, the ball has not moved. Our displacement is equal to 0. So now we can substitute those into our displacement formula, and we get c is equal to 0. And so our displacement formula is now simply x of t is minus 5t squared plus 12t. So we're asked to find the distance travelled upwards. So we know that it spent 1.2 seconds travelling up to its maximum height. And so what we're going to do is we are going to substitute 1.2 seconds into our displacement formula. And when we do that, we get 7.2. So it travels up 7.2 meters.